Hello friends, in this video I am going to discuss some more problems on Rolle's theorem. Let us consider first problem. Show that between any two roots of ex cos x is equal to 1, there exists at least one root of ex sin x minus 1 is equal to 0. Okay, now come to the solution. Let x is equal to a and x is equal to b be two distinct roots of given equation ex cos x is equal to 1. Therefore, we have ea cos a is equal to 1 and eb cos b is equal to 1. This can be further written as cos a is equal to e minus a and cos b is equal to e minus b. Mark this as equation number 1. Now, given function ex cos x is equal to 1 can also be written as cos x is equal to e minus x. Okay, therefore consider the function. Now we consider the function f defined on closed interval ab as fx is equal to e minus x minus cos x. I can define my function in this form. Okay, now we have first, this exponential function is continuous, trigonometric function is continuous, therefore their difference is also continuous. Since e minus x and cos x are both continuous, therefore fx is continuous on closed interval ab. Second is f dash x is equal to minus e minus x plus sin x. Okay, which exists finitely, which exist for every x in AB. Therefore, so fx is derivable on open interval AB. This is the second condition of Rolle's theorem. Okay, first is the continuity and second is the differentiability. Okay, now third is function value at the endpoints. Okay, now fx is equal to, fx is equal to e minus x minus cos x. This is my fx. Okay, and the interval is closed interval ab. Now f of a is equal to e minus a minus cos a, which is 0 by equation number 1, and same way e minus b cos b is equal to 0 from equation number 1. Okay, therefore f of a is equal to f of b. Okay, therefore fx satisfies all the three conditions of Rolle's theorem. Okay, in closed interval AB. Therefore, by Rolle's theorem, there exists at least one C in open interval AB such that f dash C is equal to 0. Okay, now f dash x is this minus e minus x plus sin x. Therefore, f dash c is equal to minus e minus c plus sin c is equal to 0. That is, sin c is equal to e minus c, or I can write this as, this is ec sin c is equal to 1, or I can write this in this form. Okay, this implies C belonging to open interval AB is a root of equation Ex sin x minus 1 is equal to 0. From this equation, I can write this as c is the root of this equation. I can write this. Hence, I can say Ex sin x minus 1 is equal to 0 has at least one root between any two roots of Ex cos x is equal to 1. Since a and b are the roots of this equation, Ex cos x is equal to 1, and c is the root of this equation, and c lies between a and b, which are the roots of this equations. Therefore, I can say Ex sin x minus 1 is equal to 0 has at least one root between any two roots of Ex cos x is equal to 1. Okay, hence the question. Problem is solved. Okay, now same way we consider the next question. Second question. Show that for no value of k, fx is equal to x cube minus 3x plus k has two distinct zeros. Zeros means roots of in open interval 0, 1. Okay. Question is, show that for no value of k, this fx has two distinct zeros or roots in the open interval 0, 1. Okay. We have to show this. Okay. We will start with assumption. Let if possible a and b be two distinct zeros of fx where a and b lies between 0 and 1. Since interval given to us is 0, 1, open interval. Okay, we have to show for no value of k, this fx has two distinct zeros. We start with assumption, let if possible a and b be two distinct zeros of fx where a and b lies between 0 and 1. Okay, that is f of a is equal to f of b is equal to 0, since a and b are the roots of fx. Okay, now fx being a polynomial function is continuous as well as derivable. Okay, fx is continuous in closed interval ab. Second, fx is derivable also in open interval ab. And third is f of a is equal to f of b. Clear from this? Okay, therefore fx satisfies all three conditions of Rolle's theorem of continuity, differentiability, and f of a is equal to f of b. Function value is same at the endpoints of the interval. Okay, of Rolle's theorem in closed interval AB. Therefore, by Rolle's theorem, there exists at least one C in the open interval AB such that f dash C is equal to 0. That is, f dash C is what? 3c square minus 3 is equal to 0. This means c square is equal to 1, means c is equal to plus minus 1. Okay, by Rolle's theorem, we have this type of C in the open interval AB. Okay, Rolle's theorem guarantees this C, existence of this C in the open interval AB. Okay, now this is a contradiction since we have this condition, my A and B lies between 0 and 1 and C lies between A and B. We have this, this is a contradiction since A and B and C as well lies between 0 and 1, and we are getting the value of C as plus minus 1. Now minus 1 is here to the left side of 0 and plus 1 is here. This is C is strictly less than 1. Okay. Therefore, this C is equal to plus minus 1 will not lie in this interval. Okay. These two contradicts each other. These two statements are these two statements will contradict each other. Okay. Therefore, our assumption is wrong. And assumption was A and B are two distinct zeros of fx. Okay. Now C, we are getting the values of C as plus minus 1, but C lies between 0 and 1. This is a contradiction. Hence, our assumption is wrong. So, I can write this as our assumption is wrong. So, we can write this as our assumption is wrong. Therefore, I can write as our assumption is wrong. Assumption is wrong. And therefore, for no value of k, fx has two distinct zeros, or roots in open interval 0, 1. Okay, hence the proof. Okay, now same way we consider the next question. Let a naught upon n plus 1 plus a1 by n plus a2 by n minus 1 up to an minus 1 by 2 plus an is equal to 0. Show that the function a naught xn plus a1 xn minus 1 up to an vanishes at least once in 0, 1. Okay, this we have to show. This is given to us a naught by n plus 1 plus a1 by n up to an is equal to 0, and we have to show this function vanishes at least once in 0, 1. Okay. For this, we consider the function fx is equal to a naught x n plus 1 by n plus 1 plus a1 xn by n up to a n x. Okay, we consider this function. This function is nothing but the integration of this function. A naught integration of xn plus 1 by n plus 1, integration of this xn by n, and integration of this anx. So I can write my function as this, so that after taking its derivative, when I take its derivative, I will have the form like this. Okay. Now we start with this function fx is equal to this. Now fx being a polynomial function, is continuous as well as derivable for every x. For all x. Okay. Also, therefore, I can also write this as fx is continuous in closed interval 0, 1 and derivable in open interval 0, 1. These are the two first condition of Rolle's theorem. Okay. Now, function value at endpoints. F of 0, here when I take x to be 0, clearly it is 0. And f of 1, this is a naught by n plus 1, a1 by n up to an. This is the given condition. Therefore, this is 0. This is given to us. Therefore, we have f of 0 is equal to f of 1. This is the third condition of Rolle's theorem. Therefore, all three conditions are satisfied. Therefore, fx satisfies all the three conditions of Rolle's theorem. Therefore, I can write as, therefore, fx satisfies all three conditions of Rolle's theorem in closed interval 0, 1, and hence by Rolle's theorem there exists a point. Therefore by Rolle's theorem there exists at least one C in open interval 0, 1 such that f dash c is equal to 0. This is by Rolle's theorem. Okay. Now f dash x is equal to a naught xn plus a1 x n minus 1 up to a n minus 1 x plus an. Therefore, f dash c is equal to 0 for at least one c in the open interval 0, 1. This implies the function a naught xn plus a1 xn minus 1 up to an vanishes at least once in 0, 1. This is what we have to prove. Hence, proved. Okay. Now we consider the next question. By considering the function x minus 4 log x, show that the equation x log x minus 4 minus x log x is equal to 4 minus x is satisfied by at least one value of x lying between 1 and 4. Okay. This is the problem. By considering the function x minus 4 log x, I take fx to be x minus 4 into log x. Show that the equation x log x is equal to 4 minus x is satisfied by at least one value of x lying between 1 and 4. Therefore, we will consider the function x minus 4 log x and the interval is 1, 4. Okay. Now, let fx to be, let fx to be x minus 4 log x and the interval is 1, 4. Okay. Let fx to be x minus 4 log x. Now, x minus 4 is continuous, log x is continuous. Since x minus 4 and log x both are continuous function, are both continuous for every x in the interval 1, 4. Therefore, their product that is fx, their product fx is also continuous in 1, 4. Okay. Second is f dash x. F dash x is equal to log x plus x minus 4 by x, applying the product rule of differentiation. Okay. Now, this f dash x is neither infinite or indeterminate, which is neither infinite 1 by 0 form or indeterminate 0 by 0 or infinity by infinity form. Indeterminate form. For any value of x in open interval 1, 4. Okay, so fx is derivable in open interval 1, 4. Okay, this is the second condition of Rolle's theorem. Third is function value at the endpoints. F of 1 is log 1 is 0, 0, and f of 4, 4 minus 4, this is also 0. Therefore, f of 1 is equal to f of 4. Okay, hence fx satisfies all three conditions of Rolle's theorem. Okay, clear? Therefore, there exists at least one C in open interval 1, 4 such that f dash C is equal to 0. Okay, by Rolle's theorem, there exists at least one C in the open interval 1, 4 for which f dash C is equal to 0. Okay, clear? Now f dash x is equal to log x plus x minus 4 by x. Therefore, f dash c is log c plus c minus 4 by c. Okay, now f dash c is equal to 0. This implies log c plus 1 minus 4 by c is equal to 0. That is, log c is equal to 4 by c minus 1. That is, this is equal to log c minus 4 minus c by c, or c log c is equal to 4 minus c. I can write in this form also. This implies the equation x log x is equal to 4 minus x is satisfied by at least one c, by at least one value of x lying between 1 and 4. Okay, this is what we have to prove. The equation x log x is equal to 4 minus x is satisfied by at least one value of x lying between 1 and 4. This is how we have to solve the problem using Rolle's theorem. Okay, that's it for Rolle's theorem. And in my next video, I'm going to discuss Lagrange's mean value theorem. If you have any queries or any suggestions, please write to me in comment box. Thank you.